equations. I went to my first chemistry class. And can everybody see this? And the first thing I asked in my chemistry class is, I want to know what an atom is. The chemistry teacher said that was, not in the curriculum of my first chemistry class. And he said that would be a physics question anyway. And as far as I know, we don't quite know exactly what is an atom. And that was quite disappointing for me. But he knew something about atoms. He said, there's one thing we know about atoms, that they're made out of 99.99999% space. And that kind of blew my mind. I was like, wait a minute. So what we see as creation, all the things we see, are mostly made out of space? But they don't feel very spacious. I mean, it's pretty solid. But what's going on is that there's all these fields interacting, and they don't necessarily are in perfect resonance, and they make boundaries and so on. And so it feels like it's solid, but it's mostly space. It's basically a field dividing the vacuum. And I thought, there it is. It started to match. And that was my first chemistry class. It started to make sense. Oh, yeah. Maybe we should look at the vacuum. Maybe it's the vacuum, what we call space, that has the key to creation. And the space divides itself, and then we see it as finite boundaries. Maybe the space is the infinity, and the boundary is the finite structure. The field is the finite structure. I started to see it in my head. I got very excited. And later on, I studied vacuum and, understanding of quantum theory, and I realized something. I realized something very important for the evolution of the thoughts I was having. I found that present-day quantum field theory gets rid by a renormalization process of an energy density in the vacuum that would formerly be infinite, if not removed by renormalization. Now, renormalization is kind of what they tried to do to me at school. It didn't work so good. But what it means is that when physicists start to look with the tools of quantum theory at subatomic particles and nuclear interaction and all this, they found that in order for this to be happening the way we see it happen, the vacuum density at the quantum level would have to have infinite amount of energy. That was the result of the equations. Well, equations that ends with infinity are very uncomfortable for physicists. There's two kinds of technical words in physics to describe infinities. There's one that's infinities that are normal infinities, and that's usually an infinitely small quantity. Two infinities, right? One is an infinitely small quantity, so it can easily be discarded, right? It doesn't really matter. 0.0000 somewhere down there, it doesn't matter. Okay? That's one kind of... Then there's another very highly technical term you find in physics documentation called nasty infinities. Nasty infinities are infinitely large infinities that creeps up in your mathematics, in your equations, in your conceptual physics. And those are thought to be nasty because when they creep up, it's not like you can just make like it's not there. It's an infinitely large quantity. You can't just sweep it under the carpet and like avoid the whole thing. Well, they did a real good job at avoiding this one. But in general, it was not accepted as a valid theory if your theory breaks down into infinities at its results. And so instead of discarding the concept, they did something that they called renormalization. They used the infinite potential of the vacuum and basically took the Planck's distance and took the 10 to the, what is 1.616 multiplied by 10 to the minus 33 centimeters. So that's a very, very, very small dot. Notice, though, that the 1.616 is very close to the 1.618 of the phi ratio. And they took that distance, like that very teeny point, which is now billions of times smaller than the nuclei of an atom. And they said, well, that is fundamental to creation. And if we put the number of these little dots in a centimeter cube of space, of vacuum, we will have a finite density for the vacuum fluctuations, for the vacuum density, the energy in a vacuum, in a centimeter cube of vacuum. So here it is. They took a centimeter cube of vacuum. They took a Planck's distance, bitty teeny point, and they stacked them into that cube. And then calculated how much density of these quantities would there be in there to get a finite number. The result is 10 to the 94 grams per centimeter cube. 10 to the 94 grams of centimeter cube. That's 10 to, with 93 zeros, following it. It's an extremely large number. When I'm dealing with a number that large and it came from a renormalization, my tendency is to think that we're talking about infinities. Okay? Because if you want to get an idea of what density that means, imagine you have a centimeter cube of space that has all of the stars in the universe condensed into it. Like all of the stars we see with the Hubble. Okay, all the galaxies, everything we see, we just put it all in a big trash compactor and we just squash it all up into a centimeter cube of space. All right? Imagine how bright that would be in one way. But never mind that. Then you still wouldn't have the vacuum density. You still would be short from the density of energy that is calculated to be in the vacuum at the quantum level. That is a lot of energy, folks. And so, how did this infinite amount of energy divide and create subatomic particles and atoms? To me, that was the question. To me, maybe the vacuum energy had structure. Maybe the vacuum energy wasn't just a random fluctuation like this, but had a boundary fractal structure, had a geometric structure to it. I didn't know why at the time. I didn't know how I could prove that. I didn't know how I could describe that. But I wanted to explore that thought. I started to see that maybe, just maybe, everything we see in the universe is just division of that energy density of the vacuum in various scales. To me, there was some logic to it. Well, that brought me to eventually a meeting with Elizabeth Rauscher and a collaboration with her. Elizabeth is a very respected physicist that has received medals of honor for her work in black hole physics in the 70s, has worked with John Wheeler, many other very famous physicists. And Elizabeth and I got together, and Elizabeth had written very advanced computation and mathematics for a unified field theory in the 60s and then in the 70s. And she